Okay, this is a video on section 7.8, electron configurations. Let's start out with our good friend hydrogen. Whoops. There we go. Let's start out with our good friend hydrogen. Come on. Here we go. You buy a stylus, you think it would help. It doesn't. Better off with my finger. Alright. Hydrogen. Hydrogen has one electron. Where is that one electron? That one electron is going to be in the lowest energy state it can possibly be in the hydrogen atom. Well, the value of N is going to be equal to 1. The value of L is going to be equal to 0 because that's the only available L when N is equal to 1. And we know that that corresponds to an s orbital. So, in the first energy level, that one electron will be in the s orbital. And to describe that, we draw it like this. So the electron configuration for hydrogen is 1s1, where again 1 is the number of electrons, no hashtag, number sign. S is the type of orbital, and 1 is the value of N. Now, there's another way of drawing an electron configuration, which I call an orbital notation. Your author calls it an orbital diagram. We can go with that 1s again. And we draw a line to represent the orbital. Okay. And I like to use half arrow, so I'm going to put a half arrow in here to represent the electron in the 1s. And the thing about this type of notation for electron configuration, known as the orbital notation or orbital diagram, is it shows the direction of the spin of the electron. So not only is it telling us that we have one electron, say because we have one arrow, in the s orbital of the first energy level, but it's also showing us that it has a positive 1/2 spin. So if we were going to extend this to helium, which we know has 2 electrons, where does that second electron go? Well, again, the electrons are going to fill from the lowest energy level to the highest energy level, so they're going to go from the lowest energy state to a higher energy state and so on. That's how the electrons are going to fill in any atom. So the electron in the helium atom, the first one would go in the 1s, but the second one would also go in the 1s, because remember, an orbital can hold up to 2 electrons, and because the 1s is going to be lower in energy than 2s or 2p or any of the other orbitals, that second electron is going to go there. But how is it going to go into this particular orbital? Well, according to something known as the Pauli exclusion principle, no 2 electrons in an atom can have the same set of 4 quantum numbers. So, if that's the case, our 2 electrons would both have a value of N being equal to 1, both have a value of L being equal to 0, both having a value of M sub L being equal to 0, but their M sub S obviously has to be different. It's kind of like going to a stadium to see a game or a concert or something like that. No 2 people can have the same exact 3 numbers that correspond to the ticket that they're using to get into the place, right? So they can have the same section number and they can have the same seat number, but they can't have the same row number, right? They can have the same section number and they can have the same seat number, but they can't have the same row number. Or they can have the same section number and the same row number, but they can't have the same seat number. None of the 4 quantum numbers can be the same either. So one electron has to be plus 1/2, and the other electron has to be minus 1/2. So that means that the second electron has to go into the orbital like so. In other words, spin down. So we draw an arrow showing spin down, we draw another arrow showing spin up, and there you have it. Let's do a couple more electron configurations. Something deeper into the periodic table. Okay? So, alright. Let's go into, let's say, let's do oxygen. Whoops. I hate when that happens. Oxygen. Oxygen has 8 valence electrons. Not 8 valence electrons. It just has 8 electrons, not 8 valence electrons, but 8 electrons. Sorry about that. So it has 8 electrons. I have 8 valence electrons on my mind. So in order to do oxygen's electron configuration, again, we're going to fill from the 1s, and S can hold up to 2, so we're going to put 2 electrons in there. Now we've got 6 left, and after that comes the 2s, and that can hold up to 2, so that's going to be 2s2, and now after that we have 4 left, and next comes the 2p orbitals, and remember there are 3 2p orbitals. Each one can hold up to 2 for a total of 6, but we only have 4, so we're going to put those 4 electrons in there. So if we were going to write the orbital notation for this, okay, we'd have one line for the s, and then we have another line for the 2s, and then you'd have 1, 2, we'd have 3 lines for the 2p orbitals. Okay, so the first 2 electrons, remember no 2 electrons can have the same 4 quantum numbers, so the first 2 electrons, one in this s, parallel up or spin up, one spin down. Same thing for the electrons going into the 2s. But what about the electrons going into the 2p? How do they fit? Well, there's another rule called the Hund's rule, and basically the Hund's rule says that the most stable arrangement of electrons in subshells is the one with the greatest number of parallel spins. So, if we want the greatest number of parallel spins, since we have 4 electrons here, we would have to put 1, 2, 3. The first 3 electrons would have to go in, 1 into each orbital, all having the same spin, because this is the way we're going to get the greatest number of parallel spins in this electron configuration. So, when we have 3 orbitals of the same energy, meaning that they are degenerate orbitals, meaning that they have the same energy. When you have degenerate orbitals, the rule is, based upon the Hund's rule, is that you put 1 electron in each of the 3 orbitals with the same spin before you can put 2 and 1. So we'd have to put 1 in each, and then the 4th one can go in any orbital we want, because remember, they're degenerate. They're all of the same energy. You can go into any orbital that we want, and therefore we put it in this particular orbital. We could have put it in the first one, we could have put it in the third one. It doesn't make any difference. It's up to you. But remember, we have to have 1 in each orbital with the same spin before we can put 2 and 1. Okay, so that's the rule, the Hund's rule, for putting electrons into degenerate orbitals. Alright, so let's get rid of some of this stuff here. Okay, this too. Good. Alright, so let's go back to some writing here. This diagram to the left here, see this one right here, I'm going to draw an arrow to it. There you go. It's been sitting there for a while. You've kind of been wondering, what's this diagram all about? Okay, well, as you know, in single electron systems, 2s and 2p orbitals have the same energy, and 3s, 3p, and 3d orbitals have the same energy. But you know, in a multi-electron system, that's not the case. So the question is, why is it that multi-electron systems, the orbitals in each value of n in each shell, the subshells, do not have the same energy? Well, if we take a look at this diagram, this is a diagram of radial probability versus distance from the nucleus. If we look at the radial probability versus distance from the nucleus for the 1s, we see that the maximum probability of finding the electron is right there. That's the highest probability of finding an electron, and we see the distribution of probability as we move further and further from the nucleus. And we'll see the same for the 2s and the 2p. For the 2s and the 2p, we see 2 maxima. One right there for the 2s, and one right there for the 2p. And you see that the maxima for the 2s is actually further away from the nucleus. But we also notice that there is another point of maxima, and that is also for the 2s right there, you see. So basically, there are 2 areas where we have maxima in terms of probability of finding the electron around the nucleus in the 2s orbital. So on average, my friends, on average, even though it may seem like the 2s electrons are further away from the nucleus, on average 2s electrons are closer to the nucleus because that they actually penetrate in closer to the nucleus, which can be seen by this hump of probability right there, where we reach a maximum of probability. So they may appear to be further out, but they're actually closer, because the orbital itself actually penetrates in closer to the nucleus, as can be seen by that maxima right there. And therefore, the 2s electron, on average, is closer to the nucleus. So, because it is closer to the nucleus, because it penetrates in closer to the nucleus, the orbital that is, it shields the 2p electron from the nucleus. We call that shielding. Again, it's because the 2s orbital penetrates in closer to the nucleus, and we call that shielding. So the 2s penetrates into the nucleus closer, shields the 2p electrons from the nucleus, and therefore 2s electrons are going to be lower in energy than 2p electrons. Okay, now there's one more thing in this section that we want to talk about, and it is something known as paramagnetism and diamagnetism. Okay, basically, and it's a very simple idea, if you have an element and we're going to draw 1s, 2s, 2p for some element that has electrons in the s orbitals, obviously, and the p orbitals. If you have electrons in the outermost orbitals, which are unpaired, okay, because of the Hund's rule and the Pauli exclusion principle, they're going to have parallel spins. And you see we have 2 electrons here that are unpaired. Because we have unpaired electrons, our atom actually behaves like a little magnet. Remember, the spins indicate the direction of the magnetic field of the electron. And we have 2 electrons now with parallel spins, therefore their magnetic fields are pointing in the same direction, and they act like a little magnet. And so we say that this element is paramagnetic. So it displays paramagnetism. Therefore, it will be attracted to a magnetic field. Now, what if there were no electrons that were unpaired? So all the electrons are paired up. That means all the spins kind of cancel each other out. So you've got a positive spin and a negative spin. All the little magnetic fields kind of cancel each other out. We don't have that same condition anymore, and so the element is diamagnetic. Whoops, that's not how to spell diamagnetic. That's better. Or it displays diamagnetism. And when it's diamagnetic, it's actually repulsed by a magnetic field. Actually, ever so slightly. Paramagnetic elements are attracted to a magnetic field, and diamagnetic elements are slightly repulsed by a magnetic field. Okay, so there's a couple of things I want you to look at because I want to try to shorten up this video a little bit. Look on page 308 for some general rules for assigning electrons to atomic orbitals, and also look at page 310 for a summary of this entire section. Okay, and that's it. Enjoy it, and if you have any questions, you know who to see. Bye.